Welcome. Today, let us see what planarity in graphs. First, let's see the definition for planar graph. A graph G is called a planar graph if G can be drawn in the plane so that no two of its edges cross each other. Example, K4 is planar. You can see the example for K4 which has been drawn so that no two of its edges cross each other. The next definition is non-planar graph. A graph that is not a planar graph is called non-planar graph. Let's see an example. K6 is non-planar. You can see the edges intersecting each other. Plane graph. A graph G is called a plane graph if G is drawn in the plane so that no two of its edges cross each other. Example, C5 is a plane graph. Let's see the difference between planar and a plane. A graph G is called a planar graph if G can be drawn in the plane so that no two of its edges cross each other. Plane graph. A graph G is called a plane graph if G is drawn in the plane so that no two of its edges cross each other. The graph is a planar graph but not a plane graph. Regions. A plane graph divides the plane into connected pieces called regions. See the example. Here R1, R2, R3, R4 and R5 are the 5 regions of the graph. In every plane graph, there is always one region that is unbounded. This region is called exterior region. In the same example, you could see R5 which is unbounded and it is nothing but the exterior region. The subgraph of a plane graph whose vertices and edges are incident with a given region R is the boundary of R. R1, the region R1, contains 3 edges as boundaries. Similarly, you can see R2, it contains 4 edges as boundaries. So the observation is, if G is a connected plane graph with at least 3 edges, then the boundary of every region of G has at least 3 edges. Let's see an important identity called the Euler identity. If G is a connected plane graph of order n, size m and having r regions, then n minus m plus r equal to 2. Let's go for the proof. Considering the tree first. If G is a tree of order n, then m is equal to n minus 1 and r is equal to 1. The region becomes 1. So, n minus m plus r, when we calculate, it is equal to 2. Now consider the connected graphs that are not trees. Assume to the contrary that the theorem does not hold. Then there exists a connected plane graph of smallest size for which the Euler identity does not hold. Suppose that G has order n, size m and r regions. So n minus m plus r not equal to 2 because we have assumed as contrary. Since G is not a tree, there is an edge E, there is not a bridge. Thus, G minus E is a connected plane graph of order n and size m minus 1 having r minus 1 regions. Because the size of G minus E is less than m, the Euler identity holds for G minus E. So, n minus m minus 1 plus r minus 1 is equal to 2. But then we get n minus m plus r is equal to 2, which is a contradiction. Now let's go for the next theorem. If G is a planar graph of order n greater than or equal to 3 and size m, then m less than or equal to 3n minus 6. Suppose that G is connected. If G is isomorphic to the path with 3 vertices, then the inequality holds. Assume that G has at least 3 edges. Draw G as a plane graph where G has R regions denoted by R1, R2, so on, R. The boundary of each region contains at least 3 edges. So, if Mi is the number of edges on the boundary of Ra, where I ranges from 1 to R, then Mi greater than or equal to 3. Let capital M is equal to summation I is equal to 1 to R Mi. So it becomes greater than or equal to 3R. The number M counts an edge once if the edge is a bridge, and count twice if the edge is not a bridge. So M less than or equal to 2 into M. Therefore, 3R less than or equal to capital M less than or equal to 2 into size. And so 3 into R less than or equal to 2 into M. Applying the Euler identity to G, we have 6 is equal to 3n minus 3m plus 3r, which is less than or equal to 3n minus 3m plus 2m, which is equal to 3n minus m. Solving the inequality for m, we get m less than or equal to 3n minus 6. If G is disconnected, then edges can be added to G to produce a connected plane graph of order n and size m1, where m1 will be greater than m. Therefore, m1 less than or equal to 3n minus 6. And so, m less than 3n minus 6. Hence, we have proved.